Alright, gang, here we go. This is for Chem 2, Unit 11. We're going to learn about entropy today. Really short video. Entropy is a bit of a complicated topic, but we're just going to barely skim the surface. Just enough for you to understand kind of generally what it's about and how it relates to heat is kind of the goal for this lesson. And then in future lessons, we'll kind of take it a little farther step by step by step. So anyway, so entropy... Okay, entropy can be thought of as a measure of the randomness of a system. So the more random your system can be, the more entropic it is. All right, so think about like a solid versus a gas, right? So if here's our container that has a solid in it, these particles, right? Here's our solid. These particles are very orderly, right? Nice crystalline structure. They're all arranged neatly together, etc., etc. But if we have a gas, right, these same number of particles are now going to be all over this container. I'm not going to draw the circles because I'm suddenly getting tired, but these particles are bouncing off in all these crazy ways, right? He's going here, they're going to run into each other, he's going to careen off this way, right? So gases, as an example, has much more entropy than a solid, right? Because they have much more disorder. Okay, so anyway, so that's just like the very barest bones entropy idea. An important idea about entropy is that it is a state function. So what that means is essentially, remember, state functions are things that we can measure, that it doesn't matter the path that it takes in order to get there, that the total change is always going to be the same. So enthalpy was a state function, temperature was a state function, entropy is now a state function, right? So in order to calculate entropy, just like with enthalpy, we learned 3 or 4 different ways to calculate the enthalpy of a reaction. And that enthalpy change didn't matter which way we calculated it, it'd always be the same because it was a state function. Entropy, same idea. We'll learn a couple of different ways to calculate the entropy change, but it doesn't really matter which way we use as long as we just use the tools that are available to us. So here's one way we can calculate entropy, is just taking, if we know the total entropy of the final state of it, and so we can just subtract out the initial entropy values, and then therefore we'd have that change in entropy. All right. Next guy here, next formula is that if we are at a constant temperature, and that's kind of key, is if our temperature is constant, then we can find our change in entropy by just taking the heat change divided by that temperature. And this rev thing, this means a reversible reaction. So this is something we talked about back in the previous video. Remember, reversible reactions are ones that we can simply go in the reverse, right, without it changing. All right. So this brings us to the second law of thermodynamics. We learned about the first law in the previous video. So here's the second law of thermodynamics, and it's simply that the entropy of the universe is always increasing in any spontaneous process. All right, entropy of the universe is always increasing. And so that's really what it amounts to. So in a reversible process, we get this relationship right here, that the change of the entropy of the universe is equal to the change of the entropy of the system plus the change in the entropy of the surroundings. Okay, and so therefore that should equal 0. Because it's a reversible process, that means we should be able to go backwards without losing anything. So therefore we are at 0. So as you can tell from that idea, reversible processes are pretty tricky and also a little, I wouldn't say rare, but if you really are interested in making sure you have a reversible process, you have to do some very careful planning, very careful engineering. All right, irreversible processes, a little more common, right? Irreversible processes give us this relationship, that the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings, but this will always be greater than 0, meaning that the total entropy is always going to be increasing. So there's those two ideas. So here we go. So we're going to do one practice problem here, and we'll call it good. So it says elemental mercury is a silver liquid at room temperature. Its normal freezing point is negative 38.9 degrees Celsius, and its molar enthalpy of fusion is equal to 22.29 kilojoules per mole. What is the entropy change of the system when 50 grams of mercury liquid freezes at normal freezing point? Well, so we're trying to find entropy change. So we've learned a couple of different formulas already about entropy. So I'm just looking at this, looking at what is available. Well, I know that I have my delta H of fusion, which here I can get my heat from this, my Q value from this. I just have to get rid of the moles. And then I've also got a temperature. And because I don't have a second temperature, and it says I'm at the normal freezing point, that means my temperature is constant. So the formula I'm going to use here is that delta S equals Q over T. All right, so first we got to get Q, and Q, remember, Q is just heat, so it's the energy. So we just got to get that to joules or kilojoules, doesn't really matter. Entropy, excuse me, is almost always in joules, so we'll probably just go ahead and convert that. So delta H of fusion, so that was our 2.29 kilojoules per mole. And we got to get rid of the moles. Well, it says we got 50 grams. So first, let's figure out how many grams, or how many moles of this we have. So we've got 50 grams of mercury. All right, so we'll put grams of mercury in the bottom. We're going to moles of mercury up top. 1 mole. Let's see. Let me look at my periodic table. I'm pretty sure mercury is around like 200. Yeah, 200.59. 200.59. So we'll multiply. Where did I put this? 200. So we take 50 divided by 200.59. We get 0.249 moles. 0.249 moles mercury. So that's how many moles of mercury we have. So we can multiply this over here. 0.249 moles. All right, so our moles will cancel. All right, and then we got to get it to joules, right? Because entropy is always in joules. Just because entropy changes are usually pretty small, so kilojoules will always give you a decimal. It's kind of annoying. So anyway, so we'll convert that. We know that for every 1 kilojoule, we get 1,000 joules. All right, so we say 2.29 times the 0.249 times 1,000, and we get 571. So 571 joules. All right. All right. So that's that, guy. So that's 571. And it says that our entropy change, now we need our temperature. So joules. And this guy here, we got to convert this to Kelvin. So one more little thing we got to do here. So we'll say negative 380.9 plus 273.15. Alright, so we say 273.15 plus negative 38.9. So we get 234.25 Kelvin. Alright, so we divide that. 234.25 Kelvin. Alright. And one thing that we want to think about here is the sign of that heat change. We hadn't really talked about that previously. So here for my answer, though, I got 2.44 joules Kelvin. But let's think about the heat change, the sign of this heat. Though we calculated how much heat would be evolved right here. However, we got to think about, what was that heat leaving our system or joining our system? So it was going from a liquid to a solid. So if it goes from a liquid to a solid, that means that heat has to leave the system. So remember, if something is leaving our system, it's negative. If something's coming into our system, it's positive. So really, this is going to be a negative 2.29. So that's going to be negative, which means this is going to be negative, which means that's going to be negative. All right, so we get that negative 2.44 joules per Kelvin is our total entropy change. And that's it for this unit. Nope, we got one more thing, one more bit. It says, last guy says, do all exothermic phase changes have a negative value for the entropy change of the system? So if it's exothermic means heat is leaving our system, so that means we're going to have a negative Q, right? Negative Q because it's exothermic phase change. And so we know in our delta S is equal to Q over T. So if this is negative, then that means yeah. So the answer is yes. Okay, let's see which one of these answers match up. It says yes because heat transferred from the system has a negative sign. Well, shoot, yeah, that's probably our answer. Let's double check the other yes here. It says yes because the temperature decreases during the phase transition. No. So that's not necessarily going to happen, right? We learned when we talked about states of matter that your temperature doesn't change when you have a phase change. So that's no good. And then the other two ones are no, just because we know that can't be true. No, because the entropy change depends on the sign of the heat transferred to or from the system. So the second part is true, but the heat is always negative if it's exothermic, right? So that's the tricky bit there. All right, and then D, no, because the heat transferred to the system has a positive sign, and that's the exact opposite of the correct answers. All right, so anyway, so that's it for this part here. Nice, short, and sweet. Hope you're having a great day. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.